Welcome back. Last episode, the integrating factor saved us from first-order linear equations. Today we meet a method with a completely different flavor, one rooted in geometry. We write a first-order equation in a symmetric form, m of x and y times dx plus n of x and y times dy equals 0. The central idea is that this expression might be the total differential of some surface, a function f of x and y. If it is, then f stays constant along every solution, and the solution curves are nothing but the contour lines of that surface. The level curves f equals a constant. We will learn a single partial derivative test that tells us instantly whether such a surface exists. Then we will reconstruct the surface itself, write the solution in one line, work two examples, and finally rescue the equations that fail the test by reviving the integrating factor in a brand new disguise. We close with a little history from Euler and Clairaut. Let us recall the total differential, the idea that powers everything today. Take a smooth surface, f of x and y. Its total differential df equals the partial of f with respect to x times dx plus the partial of f with respect to y times dy. This measures the tiny change in height as you take a tiny step in the plane. Now suppose you walk along a level curve, a path where f equals a constant. The height never changes, so df is 0 along that path. That gives the partial of f with respect to x times dx plus the partial of f with respect to y times dy equals 0. Stare at that and compare it to our equation, m dx plus n dy equals 0. They are the same equation if m is the partial of f with respect to x and n is the partial of f with respect to y. So our differential equation is exact precisely when there exists a surface, f whose two partial derivatives are m and n. Solving the equation means finding that surface. Here is the elegant part. How can we know a surface f exists before we go to the trouble of finding it? Suppose for a moment that it does. So m is the partial of f with respect to x, and n is the partial of f with respect to y. Differentiate m with respect to y, and you get the mixed second partial f sub xy. Differentiate n with respect to x, and you get the other mixed partial f sub yx. Now invoke Clairaut's theorem for any smooth function. The mixed second partial derivatives are equal. The order of differentiation does not matter. Therefore, if the equation is exact, the partial of m with respect to y must equal the partial of n with respect to x. And remarkably, the converse holds too on any simple region. So the test is, compute the partial of m with respect to y, compute the partial of n with respect to x, and check whether they are equal. One derivative each, one comparison. It is the fastest test in the whole first-order toolkit. One useful flexibility before we practice. The reconstruction is symmetric in x and y, so you do not have to start by integrating m with respect to x. You can instead start from the other condition, that n is the partial of f with respect to y. Integrate n with respect to y, holding x constant, and now the leftover unknown is a function of x alone, call it h of x. Then differentiate that f with respect to x, set it equal to m, and solve for h prime exactly mirroring the first procedure. Why offer two roots? Because sometimes m is ugly to integrate while n is easy, or the reverse. Always pick whichever of the two is simpler to integrate, and you save yourself work. As a bonus, if you ever doubt your answer, you can compute f both ways and check that the two surfaces agree. They must, and if they do not, you have caught an error. Once the test passes, here is how to reconstruct the surface. Start from the fact that the partial of f with respect to x is m. Integrate m with respect to x, holding y constant. That recovers f except for one subtlety. When you integrate with respect to x, the usual constant of integration can actually depend on y, because any function of y alone has zero partial derivative with respect to x. So write f equals the integral of m with respect to x, plus an unknown function g of y. Now use the other condition. Differentiate this f with respect to y and set it equal to n. Most terms come from the integral. Whatever is left over must equal g prime of y. Solve for g prime, integrate it to get g of y, and drop it back in. You now have the full surface f. The solution of the differential equation is simply f of x and y equals a constant. One line, one contour family. Let me show you the geometry on one canvas. Floating above the plane is a smooth surface. The graph of z equals f of x and y, shaped a bit like a saddle. Now imagine slicing it with horizontal planes at several different heights. Each horizontal slice meets the surface along a curve of constant elevation, and when you drop that curve straight down onto the xy plane, you get a contour line. Those contour lines drawn in the plane are exactly the solution curves of our differential equation, each one labeled f equals some constant. This is the whole picture in one image. The differential equation only pins down the family of contours, the entire stack of them. To select a single solution, you need one more piece of information, an initial condition, which is the same as saying which particular height c your solution sits at. Solving an exact equation is really just identifying the surface and reading off its contour lines. Let us do a clean one. The equation is the quantity 2xy plus 3 times dx plus the quantity x squared minus 1 times dy equals 0. So m is 2xy plus 3 and n is x squared minus 1. First, the test. The partial of m with respect to y is 2x. The partial of n with respect to x is also 2x. They match, so the equation is exact. Now reconstruct f, integrate m with respect to x, treating y as constant. The integral of 2xy plus 3 is x squared y plus 3x plus an unknown function g of y. Next, differentiate this f with respect to y. That gives x squared plus g prime of y. Set it equal to n, which is x squared minus 1. The x squared terms cancel, leaving g prime of y equals minus 1, so g of y is minus y. Plug it back in. The surface is f equals x squared y plus 3x minus y. The solution to the differential equation is that whole expression set equal to a constant c. Done in 3 short steps, no integrating factor needed. Now a slightly trickier one with trig functions. The equation is the quantity cosine y plus 2x times dx minus x sine y times dy equals 0. So m is cosine y plus 2x and n is minus x sine y. Run the test. The partial of m with respect to y, the derivative of cosine y is minus sine y, and the 2x term has no y, so m sub y is minus sine y. The partial of n with respect to x, n, is minus x sine y, and sine y is a constant with respect to x, so n sub x is minus sine y. They match, so the equation is exact. Reconstruct f by integrating m with respect to x. The integral of cosine y plus 2x is x cosine y plus x squared, plus g of y. Differentiate with respect to y, x times minus sine y, plus g prime of y, which is minus x sine y plus g prime. Set equal to n, which is minus x sine y. The matching terms cancel, leaving g prime equals 0, so g is just a constant we absorb. The surface is f equals x cosine y plus x squared, and the solution is that equals a constant. Here is a picture of why the test matters. On each side, I have drawn the vector field whose components are m and n. On the left is an exact equation. Notice how the little arrows line up everywhere tangent to a clean family of nested curves. Those curves are the contours of a genuine surface, and the field has no swirl. On the right is a non-exact equation. The arrows refuse to settle into a consistent family of contours. They swirl around. The small circular marker in the middle highlights the mismatch, the quantity n sub x minus m sub y, which is non-zero here. That quantity is a kind of rotation, or curl, of the field. When it is 0, the field is the gradient of a surface and the equation is exact. When it is non-zero, no single surface fits and the contours fail to close up. The exactness test is literally measuring whether that swirl vanishes. One trap deserves its own slide, because it trips up almost everyone the first time. After you write f as the integral of m with respect to x plus g of y, and then differentiate with respect to y to find g prime, remember that the terms which came from integrating m are already accounted for. Only the genuine remainder defines g prime. Here is the diagnostic. After you isolate g prime of y, it must be a function of y alone. If your g prime still contains an x, something is wrong. Either the equation was never actually exact, or you made a differentiation slip. That leftover x is a red flag, not something to integrate away, so build in 2 sanity checks before you declare victory. First, double-check that the original test, the partial of n with respect to y equals the partial of n with respect to x, really passed. Second, verify that your final f genuinely has the partial with respect to x equal to m and the partial with respect to y equal to n. Only then write f equals a constant. What about the equations that fail the test? We rescue them, and the hero is our old friend the integrating factor, wearing a new costume. The idea is to multiply the whole equation by a function mu, chosen so that the new equation, mu m dx plus mu n dy equals 0, becomes exact. In general, finding mu is hard, but 2 friendly cases cover much of what you meet. First, compute the partial of n with respect to y minus the partial of n with respect to x, then divide by n. If that expression happens to depend on x alone, then mu is e to the integral of it, a function of x. Second, compute n sub x minus m sub y, divide by m instead, and if that depends on y alone, mu is e to the integral of that, a function of y. In both cases, the recipe is the same in spirit as last episode. We engineer a multiplier that forces the exactness condition to hold, the partial of mu m with respect to y matching the partial of mu n with respect to x. Let us force one to be exact. Solve y dx plus the quantity 2x minus y times e to the y, all times dy equals 0. So m is y, and n is 2x minus y e to the y. Test it, the partial of m with respect to y is 1, and the partial of n with respect to x is 2. Not equal, so it is not exact. Try the second friendly case. Compute n sub x minus m sub y, which is 2 minus 1 equals 1, and divide by m, which is y. That gives 1 over y a function of y alone, so the integrating factor is e to the integral of 1 over y, which is just y. Multiply the whole equation by y. Now m becomes y squared, and n becomes 2xy minus y squared e to the y. Check exactness again. The partial of y squared with respect to y is 2y, and the partial of 2xy with respect to x is 2y. They match. Integrate the new m y squared with respect to x to get xy squared plus g of y. Matching the y partial against the new n gives g prime equals minus y squared e to the y, which integrates by parts to minus e to the y times the quantity y squared minus 2y plus 2. The solution is xy squared minus that, set equal to a constant. Let me show you that exactness is not just a calculus exercise, it is central to physics. In thermodynamics, the change in internal energy is written as temperature times the change in entropy, minus pressure times the change in volume. That combination is an exact differential, because internal energy is what physicists call a state function. It depends only on the current state of the system, so if you go around any closed cycle and return to the start, the total change is 0. Contrast that with heat. The small heat increment, temperature times the change in entropy, is not exact on its own. There is no heat function of the state. Physicists even use a special /d to flag heat and work as path-dependent, not true differentials. The point is striking. The exactness test you learned today, the partial of m with respect to y equals the partial of n with respect to x, is exactly how a physicist distinguishes a genuine state variable from a path-dependent quantity. The famous Maxwell relations are just this exactness condition in disguise. Little history. In the 1730s and 40s, Alexis Clairaut, working on the shape of the Earth geodesy, studied total differentials carefully and, alongside Euler, established the equality of mixed partial derivatives, the very fact that powers our exactness test. Leonhard Euler then formalized the criterion that the partial of n with respect to y must equal the partial of n with respect to x, and worked out the integrating factor remedy for when it fails. There is a deep idea lurking here. An exact equation is the differential equation space of a conservative vector field. When the field with components m and n is the gradient of a function f, that f is exactly a potential. This is the same mathematics that gives you potential energy in physics, where a force is conservative precisely when it passes an exactness-style test. So the humble contour line picture you learned today reappears, years later, as the foundation of potential theory. Let us recap. We write a first-order equation in the symmetric form m dx plus n dy equals 0 and ask whether it is the total differential of a hidden surface f. It is exactly when the partial of m with respect to y equals the partial of n with respect to x, which is the statement that mixed partial derivatives agree. When it is exact, we reconstruct f by integrating m with respect to x and fixing the leftover function of y using n, and the solution is f of x and y equals a constant, a level curve of the surface. Geometrically, the solutions are the contour lines of that surface. When the test fails, we hunt for an integrating factor that depends on x alone or on y alone and restores exactness, as we did with the equation that needed mu equal to y. Historically, the ideas trace to Clairaut and Euler and connect forward to conservative force fields in physics. Next episode, substitutions, we change variables to turn homogeneous and Bernoulli equations into the simple types we already know how to solve. Today we solved exact equations. We write a first-order equation in the symmetric form m dx plus n dy equals 0. The big idea is that this might be the total differential of some surface f of x and y. If it is, then df equals 0 along solutions, which means f stays constant, so the solution is simply f of x and y equals a constant, a level curve, a contour line of the surface. The test for whether such a surface exists is beautifully clean. Take the partial derivative of m with respect to y and the partial derivative of n with respect to x. If those two match, the equation is exact and the surface exists, because mixed second partial derivatives are equal. To find f, you integrate m with respect to x, then differentiate with respect to y, and compare against n to recover the leftover piece that depends only on y. And when the test fails, we revive the integrating factor in a new costume, a multiplier that, in special cases, turns a non-exact equation into an exact one. Next time, substitutions. We change variables to convert homogeneous and Bernoulli equations into the simple types we already know how to solve. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.